All right, good afternoon, everyone. Our seminar speaker this afternoon is Chris Roman. He's an associate professor at the University of Rhode Island Graduate School of Oceanography. His specialty is underwater imaging and mapping, and his research group works with multibeam sonars, cameras, and novel vehicle platforms, which is all to obtain centimeter resolution seafloor maps for archaeology, geology, and biology. He has his bachelor's in mechanical engineering at Virginia Tech, master's in mechanical engineering there as well?
Yeah, close
okay. At the University of California, San Diego. And he has his PhD from the Woods Hole and MIT Joint Program in Ocean Engineering. So without further ado, I'll hand it over to Chris.
Great, all right, thank you. Yeah, I think 2 years ago I gave a seminar, right before I got tenure, and this is actually the same talk, because I haven't done anything since I got tenure. No. So we've been pretty busy, and today is going to be an overview of the first topic here, work that one of my graduate students, Gabby Inglis here, who graduated last year, did. And so about, I don't know, 3/5 of this talk maybe is going to be basically what her stuff was. And then the other fun projects portion is sort of an update on where we are with a few projects and some things you guys might be interested in, so sort of see what happens. Mostly this is going to be sort of a pre-pictures results. If you want to learn any of the details, just things go better if you just stop and ask questions straight away, and we'll cover them, because I figured Friday at 3, people's tolerance for equations is probably pretty low. So, and then, yeah, that's me, but people who really do stuff are Gabby Inglis, who just graduated last year, Ian, Clara, Will is just starting now. Dave has graduated with a master's and now is working in the lab as a hired gun contractor, because he knows more than most everything about my own gear than I do. And Luke, who's working on the last project we'll talk about. And, oh, this just points, it doesn't.
No, there's a clicker on the side there. No? Okay.
Put the mouse on the...
Yeah, make sure it's on the presentation. There you go.
That will. Okay, that works. And now maybe this will work. Okay, perfect. So, yeah, so my background really is deep sea mapping, trying to do a lot of high resolution mapping, and I work a lot with the Nautilus program, which is, we'll see in a second, trying to really do high resolution stuff. So we're in this sort of centimeter scale from vehicles, 3 to 5 meter altitude ranges. So a couple example images. This is a couple years ago, a mud volcano site. So this map's only 40 meters by 40 meters, and the color bar there is only about 2 meters of relief. So we're approaching and trying to get to places where what we can do visually, this is a map, photomosaic from stereo cameras, and acoustically are reasonably consistent. So we're in high frequency acoustics and visual cameras. Right? Another one to show the consistency here. So this is a place we worked at many times, this Colombo volcano off of Greece. Interesting place, there's hydrothermal vents, gas bubbles coming out, fluid coming out, and we're trying to map it. So again, not a very large map, 10 by 50 meters, but getting visual, now this is stereo vision that's consistent with the multi-beam, which is jives with ROV footage from the vehicle. So again, these small scales. So lion's share of my day is spent dealing with data and students associated with this project. So this is the Nautilus project, or Nautilus exploration program, run by the Ocean Exploration Trust. So here we operate this ROV, 4,000 meter rated ROV off of this vessel. We run a campaign about 4 months a year, doing a variety of field programs. Larry's on the board of the Ocean Exploration Trust, has been working with us for a long time, and has really been instrumental in getting our new sonar system on this. So we have a nice multi-beam sonar on the ship. My focus is really the vehicle and this sensor suite that's back here. So all of my toys hang out here on the back of the vehicle. And we're looking specifically at this rig here. So we have a couple of cameras in there arranged in a stereo geometry. So these are, sort of 1 point whatever megapixel cameras. We're really not after the megapixels, but more after the sensitivity. That tends to be what you really want to go for underwater. On a calibrated rig, this is a little old now, we have about 4 cameras back there. We have a laser we shoot down to seafloor right here or right here. So we do some structured light laser imaging. We'll see that in a second. You shine a laser sheet at the seafloor, take a picture of where that laser hits the seafloor, and you can back out 3D topography very accurately. Actually, precisely, accuracy is the hard part. And then multi-beam sonar, so we run a BlueView 1300 kilohertz sonar that hangs out back here. All this looks at sort of one sample volume. So what's nice is we get everything is logged and matches in time. You get everything over the same area at the same time, so you have all the modalities in one shot. And this guy is sort of a 90-degree field of view and claimed 30-meter range, but really the effective useful range of it's around 15 meters of altitude, which is generally consistent with ROV surveys. ROVs, you're tied to the ship anyway, so you're not going to go too far, too fast. So most of our sort of marine geology surveys are in that sort of 5 to 10 meter altitude, a couple of football fields in size. We're not making any huge maps here. So some examples, again, so working a lot in collaboration with Stefan Williams from the University of Sydney, and he's in a place called the Australian Centre for Field Robotics. He's been working with us, and we've been sharing data and algorithms back and forth to do the stereo mapping. So this is a 3D reconstruction, stereo-based. So it's a fully 3D reconstruction. It's not an approximate sort of rubber sheet 2D photomosaic. It's a real 3D reconstruction. And you can get the bathymetry out of that, so that's the 3D shape. This is all with cameras now. So we've been going back and forth, working on algorithms to do this. So this is the stereo-derived bathymetry. The multi-beam bathymetry, a little rattier than the stereo bathymetry. We're trying to get these to be a little bit more consistent, so we're fooling around with the multi-beam in terms of trying to a little better range detection at those high frequencies, as well as make a map and beat out some navigation error to sort of address the navigation problem, because at these high resolutions high range resolutions, navigation error is a problem. We're going to talk about that in a second. The structured light laser system. So here is that laser off the back of the vehicle. There it is projecting on the seafloor, and you have a camera that takes a picture of that laser, and the camera image will look like that. So if the laser stripe is drawn over an object, you see how that object appears to deflect the laser. And so you can get from this image through a calibration to an actual 3D slice of the seafloor. And from that point on, you treat those 3D slices just like multi-beam sonar pings. So everything downstream in processing land from here is just treating those slices from the laser like multi-beam in sort of the 3D sense. So those are our basic sensors. And then, example of the laser here. So this guy is giving us centimeter scale resolution, or we can grid these maps now at 2.5 millimeters, 5 millimeters, something like that. So these are ancient artifacts on the seafloor, and here you can see handles on an ancient amphora, right? So you can pick out individual lips, individual handles, so you're down at this sort of centimeter scale resolution. But here, navigation becomes an issue. And if you compare that resolution to, that resolution, so this was the stereo derived, you're not getting the handles, you're not getting all that detail. The point density is too low here. The nice thing about the laser here, you have very high point density, you can keep that resolution. So we're trying to treat this like multi-beam sonar for all the sort of subsequent processing past just collecting the images. And if we do it all at once, you can sort of see how everything adds up. So you have your mosaic there, consistent with the stereo bathymetry, compared to the laser data and compared to the sonar data. So this has been very useful as a general sensor suite, comparing sort of all these modalities, what one does better than the other, how are the accuracies involved, how do they do well with navigation. That's what we're really looking at. So that's sort of the ballpark of what we're talking about. So now this is Gabby's work here, so this will be the next 20-some slides, sort of just presenting this project, right? So since we have all this data together, or these data together properly, we started looking at, is there useful ways to combine them and try and get the best of both worlds, right? So cameras are good at some things. multibeams are good at some things, lasers good at some things, and there isn't one that's great at everything. There always seems to be one that's struggling and one that's working really well. So we like to create, our goal is sort of a 3D point cloud or a gridded height map and seamlessly represent data from all of the mapping sensors, or for this one really, the cameras and the multibeam, that's the both. Get the both of them and minimize the errors in doing so, meaning selecting automatically which points to use without much user intervention. So we want to create a hybrid map using acoustics and vision in an automated fashion. Right. So we often see, here's another mosaic. This is a rubber sheet stretchy mosaic, 2D, but you can see the pretty decent quality there, nice image coverage, looks pretty good. And if you derive the stereo vision surface, you see places where the stereo vision is struggling. It's not matching points here. These can be, there just wasn't enough image overlap there. It could be the bottom was just really boring there. There's just not a lot of textural information to latch onto to create triangulations of points, right? So you have holes, you kind of get a ratty looking map. Some places it works great. So around the objects and where there's interesting stuff, you tend to do well. Right on the edges of objects, because of occlusion, you end up with some problems, right? So you can see most of the objects have a little ghosty ring around them where there's no points. So, kind of harping on this a little bit, so why try this? And you may have noticed in your life that the world is not uniformly interesting, right? So there's places where some things will work and there's places where they won't. Right? There's really interesting things out there, texturally rich places of the seafloor, lots of structure, lots of fun stuff, and there's places that are just boring. There's nothing you're gonna do about it, it's just boring, right? Flat sediment can be a problem, right? So these sensors can complement each other and try to fix issues, right? The sonar doesn't really care what the texture of the bottom or the visual texture of the bottom is. It's happy to give you nice data. The camera really wants that, right? So you can try and find ways to help each other. And the one that fish are evil. So we have a lot of problems at these shipwreck sites. A lot of fish like to call them home. So you do all this nice mapping, you get a ton of images, you get a ton of multibeam, and you're trying to do the stereo algorithms, and you end up having to throw away heaps and heaps of points because they're all transient fish swimming through. The sonar doesn't seem to be bothered as much. You can filter that out, but they can really ruin your day visually. So you're trying to make a nice photo mosaic, and you get all these stupid fish, and you just want to be able to get a reasonable estimate of the bottom topography. And an example of the camera's issues. So here's an image with good visibility and pretty reasonable stereo triangulation. This was a fish again. So they were big school of fish here, swam off, left a huge dust cloud behind, and you can see the image had not been clouded yet here, and you get pretty decent stereo triangulation, right? But where the dust cloud is, it's like, oh, game's over, right? It's like, just go home. There's nothing you're gonna do that's gonna help you here. But the sonar is not gonna care about that. It would shoot right through that, no big deal. So there's incentive here to try and merge these instruments. So to summarize, the multibeam sonar works over a little bit more range of altitudes. Cameras can be pretty sensitive because of lighting constraints, right? So you're not going to take great pictures more than a few meters off the seafloor, but the sonar's generally more tunable than that. It really doesn't care about water turbidity until it gets really bad. Right? But it's not quite as detailed. So you're not going to get the resolution because of the finite beam widths and stuff like that that you can out of triangulating stereo points if you can do them well. And the stereo cameras, they're suitable for low altitudes only. Once you get a few meters off the bottom, it gets really hard to get nice images. They're very sensitive to water turbidity, but they can be really highly detailed. You saw that stereo vision bathymetry map. That was pretty good. Looked better than the sonar did. And you get a record of visual texture, which is useful. So to approach this fusion problem, so we thought about it in sort of a couple-step approach. So the first step was sort of this data acquisition pre-processing. So we're going to have to just turn the crank on a few things straight away without really thinking about the hybrid problem to get our sort of starting point. we're going to address this navigation issue, because trying to get down to centimeter scale stuff, if there's errors in your vehicle positioning, they're going to be bigger than centimeter scale after not that much time, so you're going to have to combat that. And then you're going to have this map assembly step where you're going to take everything once you've sort of fought through your nav issues and try and populate a map at the end of the day that you hope you're going to be smart about. You're going to pick the right points and put them in the right spot. So the data bit in the beginning, so you're going to collect a bunch of co-registered sonar and camera data, camera images. Smart to try and have a decent amount of overlap. So we talk generally about 50% overlap. You want every camera to overlap itself by about 50% as you're walking forward and side to side. So it seems redundant, but it really makes your life easier if you achieve that much overlap. So we can run through the images and do some initial 3D pairwise stereo matching. So for every image set you have, you can just plow through those and try and get some terrain or some point 3D estimate for that set. Move on to your next set, move on, and just keep those sort of in the bank. And then we can process the multibeam, thinking we have these pings of multibeam. And what we tend to do is aggregate pings in a sort of a short distance. So pings between here and the other side of the room, we're going to group together and call a submap, a little patch of pings. And the assumption is over that little patch, our navigation is not too terrible. Meaning the vehicle's inaccuracy and where it is smaller than how bad the sonar intrinsically is in general, meaning the point error. Right? Once the nav error starts to grow bigger than your sonar intrinsic range resolution, you should start wondering, it's not a sonar problem anymore, it's a nav problem, right? So you bundle these things up such that you still have a decent sonar map that you can believe. Then the navigation bit, so we're going to try and refine a trajectory that we started with, and we're going to create constraints between the sensors. So we want to say, we took this image here, but hey, it was the same as this image here. Can we make a link and tie the navigation together? Right? And we're going to try and solve for all the locations of all the cameras and all the sonar pings in one foul swoop and get okay, this is where every observation was taken from. Once we have that, we're going to be smart about selecting how to populate a map of grid cells. Right? Using all the observations you have and just dumping them in there is usually not the best option. Right? So we want to be smart about that. And so we're going to come up with some criteria that try and generally move toward a higher fidelity map. So the example of the stereo vision, left image, right image, point cloud, put this in the bank. We're going to have it, so it's a little patch of 3D stereo. Right? So this is something we can automate and tune, and it generally runs as a big batch process. So we'll save all of these points. The sonar processing will run through the original sonar data, do our range detection, make a little patch of bathymetry. So again, that's like the sonar pings between here and the other side of the room, grouped together as a tile. And that's, again, a 3D thing, right? The size of this, I said before, is based on your sonar accuracy or your anticipated sonar resolution. But again, this is a tunable and totally automated thing that happens. So the navigation bit is something that most of us know, which is if you start somewhere and you walk around, this being proportional to your error, it's going to get worse. Things are going to go poorly as you go, especially if you're doing Doppler navigation. So you're only measuring velocity, depth, roll, and pitch, essentially, right? Those are your only really vehicle measurements. But if you see something on the seafloor that's interesting, you say, hey, I remember that thing, and you come around and you see that thing again, and you make a link, you make a relative observation that you can say, you know, I was 10 feet over here and I was 2 feet over here, this must be 12 feet. And you put a constraint in there, you've beat out some of this error. So now you have a way of systematically trying to remove accrued error. Right? So if you can constantly make these re-observations, you can try and beat down this error and get rid of what would have been, what you would have had you made no observations. So we do this, the engine, the math engine we use to do this is something called ISAM, the Iterated Smoothing and Mapping Approach. And this is a general topic in field robotics, marine robotics. It's this idea of how do you create an optimized engine that can run over a bunch of navigation data and a bunch of constraints and come up with an optimal mesh solution. Right? So this has been approached for about 10 years and maybe 15 years now in the robotics community, and there's lots of potential solutions. This one is sort of percolated to the top for a couple of nice reasons. It can handle lots of data points. It's relinearizable. That's a hard word to say. And it's very flexible as long as you can put the variables you want to solve for as nodes and any observations you have as links in a graph, you're pretty much good to go. You can put it into this framework and it will generate a solution for you that's going to try and minimize the errors of all the constraints you have. Right? So this is something that really exists and we're more using. This is not something we developed, but we've had to tweak it a little bit. But the details of this are pretty well spelled out in a lot of robotics literature. So for us, we're using vehicle velocity, how fast we're going, altitude, depth, roll, and pitch, a few different measurements we have. We have our unknown positions, the circles, that occur when we either took a camera picture, we took a sonar ping, or we collected a bunch of pings, right? Or we just have this navigation link, which is a measurement that says I went from here to here in between those things. So we put this all into a big graph, right? And each of the links is sort of going to be coded by where the information came from. And if you start doing these cross matches, you say, oh, I saw that thing before. What you're doing is this, which means you're really adding extra constraints to your graph. And so the kind of constraints we have would be image to image. So camera, a red one would be camera to camera. Hey, I saw this thing before. I'm here again. Sonar to sonar, if we take two of those little bathymetry submaps and line them up and tweak them, we say, hey, I've been here before. That's a blue link. And then the thing that was sort of hard about this, a lot of our effort went into this, is how do you match camera 3D shape with multibeam 3D shape? So can you take a camera to multibeam link? And that would be a red to blue link, right? So if you can assemble this thing, so here's an example of one of the links. So this would be a submap link, patch of bathymetry, and another patch of bathymetry. They overlap. You want to try and get the relative position between them, which is this link right here. And so we've done these with a bunch of different algorithms, but we tend to work on this one, the iterative closest point ICP algorithm, which is pretty popular for aligning point clouds. And so,
when you make that match, how many dimensions are you making that match?
So we do it in either two steps. We do it either in two, left, right, so it's just a slidey bit. And then what we're working on, if you can make the match, put it into your optimization and get a better prior, meaning you're closer to what you think the right match is, then you can do an ICP and get 6. Then you can try and get roll, pitch, other measurements. The trying to get Z kind of gets you into tidal corrections. You know, hey, I came across this thing. It looks like the same left, right, but there's a Z problem. Is that because the vehicle's different in Z, my depth sensor's wrong, or is it because there's tide? And so that's a little bit harder than you'd think to deal with, because you can go back and correct via tide models, but tide models aren't often what actually happened. So the degrees of freedom here in this constraint can vary. That's actually the really nice thing about the ISAM framework, is that you can put a bunch of links in that have different even degrees of freedom. You can match 2 degrees of freedom here, and the cameras give you 6 degrees of freedom there, and it generally works itself out. And then those cross-modality links look like this. So here's a little sonar patch, and there's a little section of 3D stereo points. they're the same, and ICP is trying to get you a link to make those things match up. This has been hard fundamentally because cameras and sonars aren't the same thing, right? So cameras see the surface, sonars have issues, beam patterns, they might penetrate a little bit. So whether you're actually trying to match apples and apples is debatable, but it seems like so far it seems like a constraint that's sort of worthwhile. You don't want to put wrong constraints in your graph because then you're going to have problems. But generally, it seems like this has worked out enough that it's actually useful. The hardest part of this thing is the calibrations, right? Calibrations matter a lot. So you have to really know exactly how your cameras are mounted on your vehicle, your stereo geometry predicts, your multi-beam geometry. You have a whole pile of offsets you have to sort of really nail to get this to work out.
Chris, do you do anything to the camera image to try to degrade it to the sonar capability, so that when you're trying to make the match, you're closer to apples to apples?
Yeah, that comes down to sort of how you try and implement the ICP. You can subsample, so you're trying to not overfit. You know, you don't have one cloud that has 1 million points and one that has 16. Right, and try and match them. So it kind of comes into how you implement it. And you can do that with the strategy in which you select points to match. And then you can factor in some degree of uncertainty for those points. So yeah, we do address that because the biggest problem is you end up with this resolution mismatch. That's what you'll happen to see there is things will match, and if one of them has sort of a rastery pattern and one has a raster pattern, it's a little different, they'll tend to like click. You know, it'll hop around. There'll be sort of multiple equilibria. One sort of fun thing we're working on now, well, I'd say it's more like drudgery than fun, but in this ISAM framework, one of the cool things is you can actually add a little tiny link in here that's your camera offset on your vehicle as a state that you constantly estimate. So you're estimating your offsets intrinsically in the framework. It works well for some offsets, but not all, because you're adding a lot more freedom to the thing as well. So it can go sort of terribly wrong if you don't have a good prior. Okay, so I'm just flipping around randomly. So the outputs at the end of the day, what you really have are your vehicle poses, XYZ, roll, pitch, heading, every place you took a measurement. You have an uncertainty estimate for that position. You have estimates of all the feature points where they were, all the little individual image points, right? And you have uncertainties for those things. So that's the sort of start of the third step, which is the mapping step, right? Put the stuff in the map. But at this point, you could make partial products. You could just take and say, I'm going to reproject all of my stereo data and get a map, but it's going to be that same ratty map we started with that we weren't happy with. Or I could take my multi-beam data and produce a multi-beam map. So I've used, you'd say, multi-modal constraints to solve the whole problem, and I can make individual data products. But really we're after sort of how to do it as a composite. So the thing is, you need to sort of decide what makes a good map. Do you value no holes? Do you value edges? What do you really value in terms of a map? And then try and be selective to try to incorporate data that respects those values. So your problem really here is you have a grid that you're going to call your map. You have a whole bunch of cameras and sonars floating around above it, and you need to pick what observation you're going to plug into that hole. Or are you going to average and plug them into that hole or not? Right? So the map really is sort of a 2D grid with a set resolution that you're going to try and populate. So one of the things we found out here, setting your grid resolution to something that is meaningful in terms of what the ISAM algorithm generated in terms of estimates of uncertainty of the points is really important, right? So trying to take a super finely scaled grid and put a bunch of cruddy measurements in it doesn't really work out, right? Or having a bunch of really fine measurements and putting them in a grid that's overly coarse is also sort of unsatisfying. So we tried to make those consistent. Where there are gaps and holes in the one modality, it's pretty easy to go select the other and populate them, right? What's really actually been the most useful is that if you want to get rid of outliers and errors, bad stereo triangulation points that sort of end up in very nonsensical places, you can use the multibeam to say, that's wrong, that's wrong, that's wrong. So you have this really nice error rejection. So you can use the multibeam to throw away a lot of cruddy stereo, because stereo will also be pretty good until it's really not, right? Multibeam tends to degrade a little more gracefully, and the outliers can be stereo. You can get points behind the cameras, left and right. I mean, it can be a real mess. So this has been very useful. Right? And then you can identify bad navigation links or ones that are sort of distorting the graph. So you can, once you have all these uncertainties, you can start putting points in there and say, geez, every time I put points in from this projection, it just ruins everything. So I'm going to get rid of that guy. So those have been really nice. And an example here, walking you through, okay, so here's a little photo mosaic, here's a little square we're interested in. This is sort of the naive map. If I just took all the data and threw it out there, I would get something that looks like that in terms of a 3D surface. And that's my corresponding part of my mosaic. I mean, you can see there's a lot of detail there that's just not showing up here. But if I do some outlier rejection, I can mow away all these little spots pretty quickly, right? If I start paying attention to which links tend to pollute the graph, I can do a little better. And now if I start selecting sensors where there is dense, good camera data, use it. And where there's a hole, plug in the multibeam sonar data. I can get now much better. This looks a heck of a lot better than that, right? And I have resolution now that really looks like I'm approaching something that's useful. I mean, so that's the idea. As you walk through that population step, you can do these things and get yourself a place where you're trying to use the information you have a little more optimally. All right. So another example there. So this is now reconstructed, and it's the hybrid map. And again, this little spot, the hybrid map. This is a lot more complex area. There's a lot of broken stuff here. These objects are pretty easy, or a little easier to tell how things are going, if things are going well or not. So then you can keep track of which sensor you use. So did I use the sonar or I used the cameras? So here's a map selection. So anything that was white came from the multibeam, and anything that's gray came from the cameras. So I can know what data went where, and you can see that the multibeam, the white, filled up all the holes left by the camera. It's a little harder to see, but some camera data filled up where the multibeam had errors as well. Right? And I didn't have to do any of this by hand. That's the best part, is that I didn't have to really fool around by hand here. Right? So there was zero manual input to this process. The only
something at the edges to feather, because you're inevitably, well, maybe not, but I assume you're changing resolution when you go from the camera to the sonar, or unless you're sampled at an equivalent.
If you pick your map grid size right, you don't tend to see that big jump. And if your calibrations are right, you tend not to see that, meaning there's no systematic offset between the stereo mesh and the sonar. That's the major red flag when you're like, oh, I have a calibration problem, where in the bathymetry map, if you saw ghosty changes that followed exactly this pattern, then you have to be cautious. Your calibrations are off, and that's something you have to pay attention to. At these edges, you'll see artifacts. So this was very much a hands-off process. There's some dials to turn in the individual steps, but generally, once it's running, you can let it go. So the fusion conclusions here for the first bit are so we've kind of come up with this way of refining navigation using both the multibeam and the cameras. It seems to successfully align the data in a useful way. And then we have demonstrated that we can sort of avoid many of the pitfalls that happen if you look at one modality or the other. So the hybrid map generally does seem to have some beneficial properties. Right? So those generally, so there's a lot of stuff to keep working on this. Particularly the calibrations are a real drag, and the registering between the two modalities could be better. That's the slipperiest part of the whole thing. So now moving on to the other fun stuff part of the talk. The framework is really useful, and sort of once we've got this sort of engine running, we've been just sort of throwing stuff at it and seeing what happens. And so another one, student Ian is only really worried about the bathymetry part of this. So he's been throwing just bathymetry data at it and trying to see what he can do in terms of speed increases. This is a much better framework for optimization than some other prior frameworks, like everything I did when I was a graduate student. And trying to look to see if we can create flexibility in these submap groupings, like how do we group these pings? There's an optimal way to group pings so that your constraints are all in the right spot. And so he's been looking at some data we have and looking at the differences between a sort of much more generic Kalman filter solution and a ISAM solution that should be much truer to the problem and not have as many linear estimation issues as this guy. So he's been making plots of, if you just did this, so in this plots, all you have to know is red is bad, blue is good. If you didn't do anything, you just dead reckoned, you have a lot of bad. If you go back in time and look at my thesis, you can get to this. And Ian's working on these now. He's approaching the resolution I could achieve back then, which is still winning. But my algorithm took 11 hours to run. His takes 3 minutes. So we're working on trying to improve this. Because this, in general, once we sort of get it dialed, will have a ton more flexibility than we had back some time ago. Okay, so another fun project. That laser has been pretty useful. And we started doing a lot of work at hydrothermal vent sites. And the one thing that we noticed is whenever you ran the laser over a hydrothermal vent, you get this mirage effect. You know, just like looking at the top of a candle or something, the laser would get all wispy and weird. And we thought that is really going to totally screw our bathymetry estimates. And it did for a while. But then we thought, wait a second, that's actually a useful signal. So if we can figure out where the laser is getting all distorted, it tells us where all the vents are. So that's nice. So if you take the laser and you drive it across, this is sort of a very idealized column of fluid coming up where there's some index of refraction anomaly, some hot fluid, right? The laser will get distorted when it crosses through that, and you'll see it on the seafloor. It'll make a little fuzzy spot. So typically the laser is pretty sharp on the seafloor. This is what one of those images looks like. This is actually a log intensity image, because most of the image looks totally black. But the laser there is pretty sharp, and you can do some computer vision-y stuff and extract the laser line as a single pixel per image column. But if you go over a vent, you get this mess. So this is a lot of refraction in the water column. This, there's none. This is very crisp and clear. So we've been using basically weighted moments about the centroid here to try and classify the amount of blurriness. And if we can do that, we can say, here's a place where this is bathymetry and this is venting. So here's a bathymetry map, and these are chimneys on the seafloor. And these are places where there's fluid coming out of them. So this is color-coded by blurriness, essentially. And it lets you see all the places that there's seafloor venting, right? Typically you think, yes, the venting is at the chimneys. So that's no surprise that these red dots look like these dots. But you also see places where there's venting where there are no chimneys. So that's pretty cool. So we can now have a systematic way of driving around and assessing where there's seafloor venting, which otherwise doesn't exist, short of just driving around and looking with an HD camera, which is really tedious. So we're working on now trying to estimate the size of this anomaly. Can we do some ray tracing type stuff where we try and convert what we observe here on the seafloor in terms of distortion to some estimate of how big this volume of fluid distorting it is. It seems like it should vaguely be tractable. So one of my students is working on that, and we did a test site last year. There was a little vent spitting out not a whole lot of fluid. There's the vehicle over it. There's the laser stripe on the seafloor. And we ran this, we call a multi-altitude checkerboard. So we ran over this with the laser with the vehicle, a whole bunch of different directions and altitudes to try and create some kind of a ray tracing constraint matrix. So now Claire is plowing through this, trying to figure out, can we estimate the size of the anomaly? The holy grail of this would be able to go back and say, there's fluid, it's this temperature, it's this much volume. I think we're a long way from that. But for now, we're trying to sort of see, can you reasonably back out and constrain the size of this anomaly? So you can get a rough idea. That's a big event, that's not. So Claire is working on this. We had a project I talked about, was starting when the last time I was up here, which is this Lagrangian imaging concept. This is some more computer vision-y stuff. So we built this thing a couple of years ago. It's a Lagrangian float, has some cameras that ride along it. You throw it in the water. It has a piston in it that changes its ballast so it can float around. And it'll float at some desired altitude. You say, hey, go drift at 2 meters above the seafloor, and it'll just drift there, even if the seafloor is going up and down, right? And where it's controllable down to about 1 meter. So you can say drift 1 meter off the bottom and it'll do it. And it can take pictures while it's doing that. And this sort of meter altitude is nice because it's not easy to drive an AUV or something 1 meter off the seafloor in any kind of rough terrain. It's sort of white knuckling to tow a towfish 1 meter off the seafloor. So it kind of fills a niche. And it's a lot less expensive to operate. It's not nearly as complex as a full-blown AUV system. So you can throw it out. The thing is, you can't control its destiny. It's going to go with the current, so it goes where the currents go. And some example data. We've done a lot of this off of Rhode Island. So one time we threw it out, we drifted it for 2 kilometers, took images every 3 seconds, and it was at about 1.3 meters off the bottom. And you can stitch those into a really nice single strip photo mosaic. And now this is a skate egg sacs, that's like this big. So that's a pretty decent resolution because you're so close to the seafloor. And those are stereo cameras, so you can back out the 3D shape of all this stuff if you'd like. But since you don't know how fast you're drifting, it's hard to set a frame rate. Meaning, I want to get a picture every meter, but you don't know how fast you're going, so you don't know how fast to take pictures to create that. So we're going to do visual odometry. So in real time, what we're doing is taking images and trying to estimate our velocity from them so we can predict when to take the next picture to have a whatever meter overlap, right? That means something statistically to a biologist. Right? And we don't really have any other way of measuring speed, so we'll do the camera. And so we've done this using something called featureless odometry, right? So our assumptions are it's mostly going to be flat bottom over where that one image of it. The thing is pretty stable. It doesn't tend to rock around. It just sort of drifts like this. And it only really ever drifts up, down, left, right, and it rotates. So we can solve this using image odometry in the frequency domain in 2 steps. So it turns out if you take 2 images, like these guys, and you take their Fourier transform, you take the complex conjugate of one of the images' Fourier transforms, multiply it by the other, you'll get out a result that looks like this, and it'll tell you how far one image is shifted relative to the other. Basic signal Fourier transform properties. So that's great. If you want to figure out if the images differ by rotation or scale, because your altitude's different, you can switch over to the log polar representation of an image. So you create a sort of a funny image now that's parameterized in radius and angle space. Take the FFT of the log polar image, correlate it, and you get out now a peak that tells you how the two images are rotated from each other and how they're scaled. So we've got it. We've got rotation, scale, and left and right sliding this. So we can put this into a nice algorithm where basically as images come in, you roll through this in a sort of very efficient way. Since it's all FFT based, there's no point searching, point matching, point rejecting. It can be implemented in constant instructions, like it's a constant time algorithm. You know exactly how much computation each pair is going to take. Works pretty well on cruddy images, and by cruddy images I mean maybe blurry because you're out of focus, you're just coming down to the seafloor, maybe the float is having trouble. Low contrast, maybe there's a lot of schmutz in the water. We've been doing this in Rhode Island where, you know, you guys know the thing too, coastal water is not terribly clear sometimes. It's very robust to all those sort of problems. And it's relatively easy to catch mistakes. When you screw up, if you look at the peak values of this correlation, it turns out to be pretty easy to reject erroneous matches. So we first tested this with some ROV data. So the dashed line is what an ROV did, Hercules, driving a pattern, and the visual odometry algorithm can track it. The red line tracks the blue line very well. So we think we're doing a decent job at this. Then we did it for some float data. And so then we did a survey for about an hour, drifting around with about 1,000 image pairs. And we got this. So this is now survey time over minutes, so a little more than an hour. And our velocity is like all over the place. So we thought, no, this is a problem. We totally screwed up here. Something is not working. But if you zoom in to any given part of it, it actually looks pretty predictable. So this is now speed, 0.1 meter per second, 0.05 meter per second. It actually is following a reasonably consistent pattern. And if you use the estimate you had and you put together a mosaic using them, you say, yeah, well, it actually did do that. So the lesson we learned was, one, the good part was we can do this. The naive part was currents a meter above rough bottom are not trivial. Like the assumption that it's just this nice steady advection is sort of wrong. We've never found a place where it was nice and steady, even over relatively flat bottoms. We've always seen some bottom turbulence that's moving the float around, or we've seen wave surge, you know, in 30, 40 meters of water. So now we're thinking we have to do a lot more averaging in here to try and get an average speed, because doing it image per image or doing it in batches is actually proven to be hard, mostly because the world is just more complicated than we had hoped. All right, the final fun project of the day, which has applications, I think, to some of the work people do here in terms of water column, bubbles, and multibeam, and a lot of work that's sort of recently started in terms of looking at the fade of things like methane in the water column. So we built this thing, which is a profiling vehicle in the last 2 years, and just finished some tests with it. So it's basically a vehicle that's got some wings on the side. It slides up and down a ship cable. And so we'll explain the motivation here in 1 second. So we're looking at trying to get oceanographic cross section. So you want to get like a temperature salinity plot over a distance, right? Your nice sort of shower curtain plot of what's going on in the ocean. People have done this for a long time, and there's a family of vehicles that does it called undulating tow bodies. So these things have wings, you drag them behind a ship, and they basically just go up and down like a sewing machine as you drag them. They're remote controlled. The downside of these guys is, since you're dragging the cable with you, you're pulling this thing through the water with the cable. It's got to pull all that cable underwater, which limits how deep it can go. They only go to a few hundred meters before they sort of crap out. And the glide slope, which I'm going to say is the ratio between the speed this way and the speed this way, they tend to be like 5 this way and 1 this way, 5 this way and 1. So the sine wave, although you put it on the plot and it looks really coarse, is actually almost a flat line. It's really sideways. So an example here, New England shelf break front with this version of that. This vehicle did these profiles and created this section. But you look at the section, you see there's a lot of interpolation. Like most of this structure is all interpolation here. Doesn't look terribly convincing in that direction. Underway CTD you might be familiar with for multibeam systems. These have become popular. Keep repeatedly chucking a CTD to do sound speed. Ray tracing, same issue. These guys can create sections that, or profiles you can turn into a section, but they're limited in how fast you can throw this thing over the side and reel it back in. The wire flyer idea, you put a cable out and a big fat weight on the end of it, and you don't fool with the weight, you just tow it, and you let the cable take a certain shape. And then the vehicle is autonomous, and it can just slide up and down the cable. The cable goes right through the vehicle, and the vehicle uses its wings, and it can drive a sinusoidal pattern up and down. And we've succeeded now, we've got the cable off the vehicle, so now the vehicle no longer has to drag all that cable with it everywhere it goes. So it's a lot more free. And it can go a heck of a lot faster, and it can make these glide slopes now approach 1-to-1, meaning I can go up as fast as I can go forward. So I'm getting automatically 3 to 6 times the resolution in the horizontal direction than one of these guys can achieve. So I'll put together, there's the vehicle, there's the wings, there's a modem on it, there's a CTD, there's a fluorometer, there's an oxygen sensor, like all that fun stuff. And there's your clump weight, the big heavy thing that sits at the bottom, right? This is us putting it off the ship last year. You lower the clump weight in, you can set that down at a depth, then the vehicle you can basically set it profile between these two depths at this speed, and it'll do it. And if you look at any of the data in detail, this bottom plot first, here's the clump, how deep it was, and here's the vehicle oscillating up and down in the water between 200-ish and 350 meters. So this is, right now, even that plot is below what most undulating tow bodies can do, right? And then this one is cable angle, so you know that if you tow a cable from a ship, it tends to walk back on you, right? And so the vehicle has been successful at climbing up cables that are walked back as far as 45 degrees, meaning the cable's pretty swept back, right? So the vehicle, that's like basically a sailboat sailing upwind. So it's sort of analogous to about a high-performance sailboat sailing tight to the wind is what this thing can do. And we can give it specified velocities, the red line, and say, go do those. And it can, to some degree, do it and do it. So you can say, I want to travel at 2 meters per second, and it can do that in a closed loop fashion. Some of our performance issues here where we're not quite getting it chalked up to sort of our first cruise and not wanting to break anything. So we think we can do a lot better here because we had a pretty wimpy control algorithm running this thing. But now we can create sections of the ocean that look like this. So this is a comparison between underway CTD data down to 250 meters as fast as it could chuck it. And then that's the flyer. That's the vehicle doing the same thing. So you got 4 times the resolution that you had with this thing, right? So that was encouraging. And you can clearly see, you get a lot more resolution. This was the New England shelf, so this is the edge of a ring, and this is shelf water over here. If you go a little deeper, 200 meters to 400 meters, this is the block the flyer profiled. And these are all the flyer tracks versus what the underway CTD could do. Because as soon as you start throwing the underway CTD deeper, it takes longer to get down there, it's falling slower, you gotta reel it back. So your long track resolution starts to degrade pretty quickly. So we're able to get quite a bit of resolution down there. And then a plot much deeper, so now between 500 and almost 700 meters, we can get that same resolution. These are a subset of the vehicle tracks laid on top here, superimposed. And this was profiling up and down at 2.5 meters a minute. So this is also faster than you can run a CTD winch. We've seen a little bit of stuff that's speed related in the data. You can see this sort of little pattern in the CTD data. So we're working on correcting some of the CTD data for lag in the pumping system because you are traveling very quick. So with any luck, we can tease out and get rid of some of this. But you're getting a resolution down this deep that I don't think is otherwise achievable using Toyos or anything else, right?
Get your temperature inversion there on the left-hand side?
In here?
Like a density inversion? It's kind of interesting.
Yeah, this was so this was underneath of this. So this was right where the ring was hitting the slope, which was one of the motivations for this project was the physical oceanographers were kind of into this for mixing and filaments and all kinds of layering stuff. So there was all kinds of wacky stuff going on. We were chasing through here. There's this very weird pattern in here. I don't think I made any density plots to look for just stability. I was just making sure the vehicle is working, honestly.
What kind of turnaround time, if you go back a slide?
Yeah, sure.
Get in with the UCTD.
Off the top of my head, I'm not 100% sure. I don't think I have anything in terms of time with the UCTD. But this was set up for that depth, to go as quick as it could. And this was comparable ship speed of 4 knots, I think. So we ran the ship at the same speed for both tests. We had the UCTD going as fast as it could. UCTD you can do 2 ways. You can either wind the tail or not. You can wind the tail to go deeper, but you gotta wind the tail, so it's a lot slower. So this was a non-tail wound, just get it over the side as fast as you could. So this has been a fun project, and it seems encouraging. So this is a thing here where this kind of resolution is not otherwise achievable in the deep ocean, and based on some work we've done, vent plumes and things like that, gas bubbles, running a vehicle like this and trying to make it look consistent with water column multibeam, I think would be very interesting, depending on the sensor package you put on this thing. Right now we have a CTD, fluorometer, oxygen, but there's no reason we couldn't put chemical sensors on there, or side-looking acoustics, talking to Tom Weber and Val about that a little earlier. So our application areas we're looking, you'd say maybe for customers, are sort of in the vents and plumes, mixing at the fronts. We're trying to go back to the New England shelf break front next year and do some stuff where the front hits the shelf, because that's really otherwise hard to observe. And plankton layers. So with the fluorometer, we can get some really nice images of plankton aggregations. Yep.
What's the maximum depth you think it would be useful at this point?
This thing is rated for 1,000 meters, but the nice thing about the concept is it's not depth. There's nothing in here that depends on depth. So you could make a 6,000 meter version of this thing, because once you're not dragging the wire around, it doesn't matter. So we do have a proposal in to build a 4,000 meter one. So you could do this very deep near bottom plumes, it doesn't matter. There might be some ultimate limit on how fast you can drive a ship with that much cable out. But the nice thing about that too is cables tend to get slopey at the top, and as you get to the bottom, get steeper. So if you want to work in the deep ocean, working on the steeper section, the cable is easier. And rarely, you don't really often, I think you want to use this as a targeted thing. I want to look at this depth window, and you probably wouldn't be running the thing from top to bottom in the ocean. So, but there really is no depth limit on it. That's the really nice part about it. And compared to the pain and suffering of doing CTD toyos that deep, which is like mind-blowingly boring, you can get a lot more resolution. So I mean, these are our sort of application areas. We need to look a little bit into the CTD data lag, mostly because we're just using it with a different plumbing system than most everybody else does. So we got to sort of tease out. I think that's a solvable thing. And then we could do a lot better, I think. Our performance was reasonable. I'm happy with it, but it was also kind of wimpy. We weren't really swinging for the fences. So I think next cruise, we're not as afraid of breaking it. We can go out and improve our performance. So acknowledgements again, this is the end. All this stuff I do vicariously through my students. The Hercules operation team runs the vehicles at sea, and we get a lot of support from them and then all the various funders. So thank you. I'm happy to take questions. Larry?
What sort of motion sensor are you using on the vehicle?
So we use the octans for heading, pitch, and roll. Use the Doppler 600 kilohertz for velocity. We don't have them plugged together, like a lot of people running the hybrid INS version, where you take a fins or octans, plug your Doppler into it. We've been talking with Val about this, my student Ian. Our algorithm starts practically at F equals MA, in the sense that we take the raw velocity measurements, the raw altitude, or the raw attitude measurements, and build it all up from there. we're thinking about trying to come up with a reasonable approximation where you start with some INS track. You don't have to go back to raw individual measurements, but still get something useful out of it. So that's an ultimate goal. Yeah.
Shahak has a question. He's tuning in remotely,
Huh?
and he asks, could you elaborate on how the laser profiler works? Is it measuring a deviation from a straight line and translate that to a Z-based projection? Z-based based on projection calculations. Does that make sense?
Yeah, he or she essentially. I didn't catch you.
It's a he.
He.
Shahak.
So he's got it. Yeah, he's got it right. So if you back up, maybe this picture is the best. So here's your geometry. So you have a camera looking down, and you have the laser, which if it was a flat seafloor would draw a stripe. Right? So there's a relationship between where the laser stripe appears in the image and the distance. So if the seafloor came up, you'd think the stripe would move down the image. The seafloor goes down, the stripe moves forward in the image. So when you go here, all these little wiggles convert to basically Z, a depth estimate. And you have to get there, you need a calibration, which is you need the geometry of the laser plane in the camera frame. Because basically what you're trying to do is find where a ray coming out of the camera through that pixel pierces the laser. And that's your answer for that pixel. So that is how it works. We've been doing this and we've been able to grid things really pretty precisely. The accuracy is the hard part. Calibrating the thing is not super trivial. It's easy to be close to right, but knowing that you're really right is harder. Mostly because cameras with flat viewports, this is my assumption at this point, or my theory, cameras with flat viewports violate the pinhole projection model that you're trying to use to calibrate the thing. So it depends on how far you get from that before you have issues. So, but that's generally how it works.
And I guess his follow-up question is, does that laser profiler comprise some of the stereo imagery? So is it filling in some of the saturated pixels in the imagery?
No, so we haven't actually used, in that multi-fusion thing, we have not introduced the laser bathymetry, which we eventually would like to. The benefit of the laser bathymetry, it gives you super dense point coverage. So without having to do dense stereo. So to doing dense stereo, you have to do all this dense stent matching, and you don't tend to get as dense a coverage. With the laser, you get, for free, very dense 3D reconstruction. What we like to do is then paint the images on top of it. So you get that super dense, like point density is crazy high. It's 10 points per square centimeter or something like that. But then be able to project the imagery on top of that, and then you really have something that's pretty nice.
What's the frame rate of your camera for that?
The laser we run at 20 to 25 frames a second, and when vehicle moves at about 15 centimeters a second. So you get 2 pings per centimeter this way, and per ping you get a few points across the camera, left and right. So you're in the 5 to 10 points per square centimeter range.
And what is typically the footprint of the laser beam on the,
It's about
on the target?
In the camera, it's about 3 pixels. So it's sub-centimeter. And then when you try and convert this thing to find the peak of the laser, exactly where the laser was on the seafloor, you can do sub-pixel interpolation. So if you just drew a stripe down your image, you'd see the laser took this pixel, this pixel, this pixel, this pixel. But then you fit something to it, and you say, that was the peak. And that lets you get below pixel resolution, range resolution, so to speak. But still, you're fundamentally finding below a centimeter. You're starting at the crudest with about a centimeter. So,
Does the accuracy of that system allow you to constrain the DVL, like have a feeling for what the uncertainty is in the DVL, the real sort of uncertainty is in your velocity measurements? Like, can you overlap in such a short period of time that you can know what your actual
right.
was?
Meaning, I had a dead reckoning track that went like this. I did all this stuff. How different was it? Yes, you can do that. Whether there's so many confounding factors in doing that, it'd be hard to tell which is which, or I'd have to, someone smarter than myself would have to really scratch their head and figure out how all those things, which one is really driving it, and could you blame all of it on the DVL, so to speak, the randomness of or is it just the fact that your heading offset is wrong? Those errors often mask each other, so it's not easy to tease out who's causing what problem, because a lot of errors cause similar results.
Just when you put together your composite bathy maps, do you find that the accuracy of the various systems are about the same, so that you don't have to compromise on resolution, or do you find you have to compromise on a single resolution that's maybe slightly better than one sensor and slightly worse than the others would be able to achieve on their own?
Generally, they've been reasonably consistent with the stereo terrain. The number of points you get out that you believe from the stereo terrain tends to be similar to some degree as the multibeam. So you don't have that problem. If you were going to go and do this with the with the laser, you would have that problem for sure. Because then you'd basically totally polluting one for the sake of the other, which isn't a great trade-off. Thus far, it seems like things are reasonable.
And have you theorized a solution for how you'd want to tackle them?
This one, no, not exactly yet. Mostly because this one, the calibration is a little bit of a sticky thing, and it's pretty. I mean, I don't have to do it to know that the first thing I'm going to run into is a calibration problem, because we're having enough trouble making this guy self-consistent over larger scales, much less consistent with all his neighbors. I think it's real. I think eventually that's the way we want to go, right? Because you want to be able to, in a unified way or intelligent way, exploit all the resolution you have. So, question?
Yeah, I was wondering. So, is the method of figuring out the navigation, is this like an alternative to sort of baseline acoustic pingers, or could it be improved by that, or is it better than that already?
So this is so what we're talking about here is refining a dead reckoning track, meaning there is no external reference. You just say, I'm starting here and I'm just getting this track, and it's all integrated error. If you want to then throw in external measurements, a ground referenced external measurement, either from a USBL or a transponder system, the nice thing about the math works out that you can have this sort of grid hanging out here and then try and anchor it in various places to the ground. So in theory, it should work out that, yes, that will help you and complement what you're doing filtering-wise. So what you're really trying to do is get this super self-consistent thing that's the most consistent among all the constraints you have. But fundamentally, it could slide around in the world. I could start this whole process and be 10 feet off to the left. Everything is self-consistent. But if I start anchoring it to the world with a USBL or transponders, in theory, it should all work out, right? But that's what you're talking about, hybridizing the solution. You have some dead reckoning with some ground-based fixed reference.
Yeah.
And that just really depends on where you draw a stake in the sand. So here, which you'd be just taking this map, this thing here, which is not anchored to the ground. It's floating around in space, and drawing an anchor, saying that's an LBL or a USBL measurement. So it should support that. My students started to do that because we did rent a nice 200 kilohertz LBL system for some shipwreck work we did last year, and he's been looking at trying to do that. How to anchor everything in a seamless way. So if you do have these, I mean, you don't want to. If you have the operations, you want to be able to use it. You don't want to throw it away, right? So we've been looking into doing that.
So I guess shipwreck mapping is one of the main applications. Could you talk about other applications that might be benefit from this?
Sure. Our history is started off with shipwrecks. We're working a lot in the Mediterranean with the Nautilus program, but doing a lot of this work we found to be very helpful. One of the things we noticed at this site. It's pretty cool. This was a density-driven flow. So the bacteria are mapping out essentially riverine channels. And so we were trying to map and get an estimate of the flow, how much flow is going downhill, and trying to beat out the resolution that we could actually get down to the centimeter and see these, what's the sort of riverine system for laying out the bacteria. And then we went back year to year. We actually surveyed that place 2 years in a row. And it was really neat to see the change in pattern, how much variability there is. So it seems like, to me, my naive, not being a geologist, is that if you have the resolution, very few people will turn it down. And we've always generally been able to find some interesting way of using it. So now our program in general is moving more toward ocean exploration, a little away from marine archaeology. So there'll be more and more applications like this. And the big one really is change detection. So year to year this, or we're going back to the CCOM-JHC volcano off of Grenada. And big thing, can you correlate that if there's any inflation or deflation? Is there any change detection type stuff you could do? It'd be really nice to have this working out. So I think that's the big application. Yeah.
I saw an interesting application in our last AV boot camp, actually. We had nowhere near a sophisticated method, but kind of a manual method of matching overlapping lines. And there was a surface ship out that was tending the AUV, and they lost their RTK corrections for their navigation, so they were just using differential GPS. And the guy who was doing the did matching of their data, overlapping surface ship data, and found really big differences in overlapping lines to several meters, approaching 10 meters in some places, amazingly. So he was correcting non-RTK positioned surface navigated multibeam data with itself to create a better map that wasn't as blurry, to make it look like it should have looked if you'd had higher navigations. And I thought that was an interesting, I didn't expect those errors to be so big and it to work that well, but it did.
Yeah. So I think there's lots of applications for it. The change detection thing, and then I think going back to the resolution thing that Larry and Brian brought up was, we're working down the road of more adaptive surveying, and can you map an area at this altitude? How interesting is it? Is it worth going down to this altitude? And now how do you incorporate that seamlessly? So I think at least some bits of this should be relevant to that project. Gotta find out which bits. That's the hard part, I guess.
Did you go for trials on perfectly controlled targets in a perfect environment? I mean, for instance, on the floor of a dry dock, disposing geometric targets?
Unfortunately, no. The best we did was last year when we rented that LBL system, so that's what we're trying to compare. Considering that is the gold standard, or to try and figure out how egregious some of our navigation errors are. I have tried to put targets on the seafloor before for doing some calibration stuff. It's really hard to get a decent looking target on the seafloor that images properly, acoustically and visually. And we tried with some fiducials at some of the wreck sites before, and was never convinced that even the targets you put down, we were going to be able to resolve any better than we could anything else. So I go back and forth on how much effort I want to put into some of that. But right now we're at the point where, I mean, we're correcting errors of obvious inconsistency that we can reasonably convince ourselves we're doing better, especially if you make plots like, it must be time to go. You make plots like this one, which is basically, if you have all these data where you've overlapped a bunch of points, you can sort of look at how thick the point cloud becomes when you say, I map this, then I map this, I map this. It's like laying pieces of paper on top of each other. If you color code the pieces of paper and start measuring what's the total thickness between each individual piece of paper, you can make maps of error. And we sort of believe this is true in the sense that beating out this calculated error, we're seeing improvements in the algorithm. So we think we're approaching the correct answer. But yeah.
Well, thank you, Chris.
No problem. Thank you.